if we have a light wave, or, well, let's think of a light wave. A light wave, traveling from one medium into another, where in the second medium the speed of sound is less than in the first, then what's going to happen to the frequency and wavelength of the light wave? Well, what happens to the frequency is that it remains unchanged. The light wave is being driven, and what we have here, we haven't really gone over the nature of the light wave, but it's an electric and magnetic field oscillating back and forth. When the light wave is moving in this direction, the electric and magnetic field are both perpendicular to one another and perpendicular to the direction of the motion. If we just think of the electric field is being driven up and down to maximum and minimum with a certain frequency here. That's not going to change when it goes into a new medium. But what does change is how fast the object or the wave travels, which means that if the frequency doesn't change and the wave slows down, the wavelength is going to decrease. Okay, so we see that the frequency is unchanged. Velocity decreases by a factor n2 over n1. Now let's look back up here at n2 and n1. The velocity is inversely proportional to n. So if n2 is bigger than n1, the velocity will be less by factor n2 over n1. And we'll talk more about that. These n's are called the indices of refraction. If v decreases by factor n2 over n1, then the wavelength lambda decreases by the same factor. Now, if you decrease by a factor n2 over n1, you change by factor n1 over n2. If you decrease by a factor of 2, you change by a factor of 1/2. So that the wavelength will change by the factor, simply the ratio of the two indices of refraction, which is reciprocal to the ratio of the velocities of light in the medium, as we've seen in the general physics course. Okay. So, if we go from air where n is very close to 1, or vacuum where n is 1, into a region where we have an n2 that's greater than 1, and there's no n2 less than 1, then if we have wavelength lambda naught here, the lambda here will be lambda naught over n2. Lambda will simply decrease. It'll change by the factor 1 over n2. And we'll see why this happens later. But when light goes from medium where the index of refraction is n1 to medium where the index of refraction is n2, with n2 greater than n1, I should have written here that n2 is greater than n1, but keep that in mind, n2 is greater than n1. Like light traveling from water out into air. Then, of course, you're familiar with Snell's law, but we want to talk about the fact that, okay, if we have a ray here, it'll be refracted away from the normal. A ray here will be refracted even more away from the normal. This red ray is refracted so much that it stays parallel to the surface of the water. And this green ray, which comes in at a greater angle of incidence, will have to be refracted even more. Well, it turns out that it isn't refracted because it can't refract anymore. It's not even leaving the water. So what happens is it's reflected at the surface of the water. Totally reflected. None of this green ray gets out of the water, assuming the water surface is smooth. The shark hasn't gotten here yet, so the water surface is still smooth. So that the angle of incidence equals the angle of reflection. Now, at what angle does this happen? Okay, this is called the critical angle, depicted by this red situation here. Okay, well, the sign of the critical angle, the angle of incidence of the critical angle is just theta critical. The angle of refraction is 90 degrees because it's being refracted at 90 degrees to the normal. So say the sine of theta critical over the sine of 90 has to equal n2 over n1. Snell's law says that the ratio of these sines has to be n2 over n1. And that implies that the critical angle is the inverse sine of n2 over n1. That's the critical angle at which total internal reflection occurs. We talk about a little bit about polarization. Different colors of light have different indices of refraction. red light is refracted less than blue light. So if we have white light coming into a prism, you can see where the normal is here. The white light's going to be refracted closer to the normal. And then we get here and it's going to be refracted away from the normal at this surface. If the blue is refracted more than the red, then the blue will end up here, the red will be here. We have a little terminology. This is called, this is the angle of deviation of the red light. The angle of deviation of the blue light would come on down to here. And the angle here, the angle between the red and the blue ray, is called the angle of dispersion, or a measure of dispersion.